When we migrate from Newtonian to relativistic physics, Newtonian world to the relativistic world, many of our ideas need modification. Idea of mass needs modification because now we have two different types of mass. One is the relativistic mass, another is the rest mass. We have to modify our idea of length. That means if we have two reference frames, in one reference frame, I am there in one reference frame. My friend is there in another reference frame. And suppose there is a rod which is at rest with respect to my frame, which is the S frame. I'm measuring its length, and also my friend who is in the moving frame is also measuring the length of the rod. The rod is at rest in my frame, and my friend is in the moving frame. So he will measure also the length of the rod, and his measurement will be less than my measurement because length will be contracted. So idea of length will be modified. Then the idea of momentum, that momentum is conserved in interactions. That idea of momentum is also changed because now we have to multiply with the Lorentz factor. You can absorb the Lorentz factor in the mass, and then your rest mass will be multiplied with the Lorentz factor, and that product will be the relativistic mass. And then again, time dilation. That means I'm in S frame, my friend is S prime frame. S prime frame is moving away or it is coming towards the S frame. I am measuring the time in S frame in a clock which is at rest in the S frame. Then my measurement of time and my friend's measurement of time, who is moving with respect to S frame, his measurement of time will be different because he will experience time dilation. Clock which is at rest in the S frame, he will be running slowly with respect to my friend who is moving when we migrate from Newtonian world to the relativistic world. Idea of mass, length, momentum, time, they all need modification. But we can still use the concept of work, which is force multiplied by displacement. So let us try to work with this integral, force multiplied by displacement. Now you can rewrite it as dpv, and then we have to integrate this w. Then we get the kinetic energy. Kinetic energy is this integral 0 to v. So this is, we can do this integration by parts. This is v is first function unchanged into integral the second, mv square minus mv dv. And here again, we express in terms of the rest mass m0, then the Lorentz factor is within the integral. And how to do this integral? Put this 1 minus v square by c square as z. Then dz will be minus 2v by c square dv, so multiplied with c square by 2. Then we get mv square plus m0 c square by 2 dz by root z. This is root z. And what about the limits of the integration? For 0, this is 1, and when it's v, 1 minus v square by c square. Let's do this integral. Then we get mv square plus m0 c square. Here we have put the limits. So we can combine these two terms. Then we get m0 c square by root over 1 minus v square by c square. Minus m0 c square. That means mc square minus m0 c square. That is the kinetic energy. Because this is work, this is kinetic energy. So this also is energy. And we say this is the rest energy. That means mc square minus rest energy will give me the kinetic energy in the relativistic case. So that is again slightly different from the classical expression of half mv square. We can add kinetic energy plus m0 c square we have mc squared. So that means that E that we have in E equal to mc squared, that quantity E is the kinetic energy plus the rest energy. Okay, so this is E equal to mc squared. So this is Einstein's famous equation, which is probably one of the most famous equations in physics, and it relates mass with energy. Next, let us square this. If we square this quantity, then we get E square equal to this E square V square by C square plus M0 square C to the power 4. M equal to E by C square, then momentum will be EV by C square. So E square will be P square C square plus M0 square C to the power. For a massless particle, for example, for photon, it does not have mass. So classically, we cannot expect that it will have momentum. But here we see that even a massless particle like photon will carry momentum. It will transfer momentum. That way it will exert pressure. For example, to trap and manipulate microscopic particles in the nanometer scale. This can be used in optical tweezers. I suppose that was interesting, and thank you for watching.